It is part 2 of section 3.5, cubic splines. We first recall the definition of cubic splines. Function S is a cubic spline on the interval a to b if these three conditions are satisfied. Domain of the function is the interval a to b. Given a partition on each subinterval, the function is a cubic polynomial. S prime, S double prime are continuous on the interval. The key idea for the construction of cubic splines is quite similar to that of quadratic splines. Let's see this remark. On each subinterval, we have to determine coefficients of a cubic polynomial of the form. The coefficients are ai, bi, ci, di. So we have 4 unknowns in each subinterval. There are total n subintervals, so that we have to decide 4n unknowns total. On the other hand, equations we can get are here for SI, and SI is continuous and it is interpolating the data points. For each subinterval, right edge value and left edge value will make equations. So for each subinterval, we have 2 equations, so that total 2n equations are available. For S prime, its continuity can be enforced at interior points and n-1 interior points. So we have n-1 equations. For S double prime, also its continuity can be enforced n-1 interior points. So here we have another n-1 equations. However, we have only total 4m-2 equations. 2 equations are missing, so the user should provide extra 2 equations. We'll see examples of such additional equations. Here we have the algorithm for the construction of cubic splines. Similarly, as for quadratic splines, we define Zi is same as S double prime at Xi. We'll decide later on this value. Now, Si is the restriction of S on ith subinterval. Si double prime is a linear function because Si itself is a cubic polynomial. After the double derivative, second derivative, we have linear function. Now, Si is defined on here ith subinterval xi-1 to xi, and Si here, and double prime is also here. At the left edge point, the value must be Zi-1, and at the right edge point, the value must be Zi. That's from the continuity of S double prime. Now, because it's linear on each subinterval, we can construct the linear function connecting the Zi-1 and Zi. This is the result, which is Lagrange form of interpolating polynomial. Here HR is the interval length, Now, from this equation, we can get SI by integrating twice. Then, and after integration, we'll get integration constant. And one more integration later, the extra term must be a linear function. Now, we write down the linear part in this way. And here we have to decide C and D. Now we'll use left and right edge values for SI. SI is defined on this ith subinterval. We are using left edge point and right edge point. And we already know the value here. That is interpolation property. And we use here x is xi minus 1, and then this term, that term will be 0, and these two can be simplified in this way, and that is the same as yi minus 1. Similarly, when x is xi, then this will be 0, and that will be 0, and we can simplify this one to get this one, and it's the same as yi. So we can solve for C from here. We can solve for D for this equation. So we can get C and D and use the solutions to finalize the formula here. So SI can be obtained by using this formula. Now we have to decide the z values. Okay, and among the z values, z1 to zn minus 1 can be decided from the continuity of S prime. So we differentiate it, then we recheck this one, and we plug xi, then this right side can be simplified in this way. Okay, now we need that one. Okay, let's see here the picture. That is xi. Now that is here xi minus 1. That is xi plus. Okay, I'll make a picture a little bit better way. Okay, that is here xi plus 1. Si is defined here as I plus 1 is defined here is prime also. So that Si prime at xi must be same as Si plus 1 prime at xi. At this point, the derivative of this one and derivative of this function, this portion, must be the same. So we have to evaluate Si plus 1 prime at xi. Okay, we can get S prime I plus 1 from this one with I replaced with I plus 1. Then we can get Si plus 1 prime, and we use xi. Then we can get this right side. So these two should be the same. With a little bit of algebraic manipulation, we can get this equation. But this one is available for only is 1 to n minus 1, the interior points. Okay, so now, but unknowns are z1 to zn, n plus 1 unknowns. So we need 2 extra equations. And you may try to give z0 and zn left edge point, left end point, and right end point. We may assume that the second derivative is 0. Second derivative is 0 means that and outside of domain, we may assume the solution is linearly changing, so the derivative, second derivative is 0. It's quite natural assumption. So once you are using these assignments, then the cubic spline is called the natural cubic spline. If we know the slope values at left endpoint and right endpoint, then we can use these slope values. In this case, the spline, cubic spline, is clamped, so that here we have a clamped cubic spline. For natural cubic spline, here quite easily you can make the algebraic system out of this one, because Z0, Zn equals 0, and you can have this linear system. Now there's matrix A and vector, unknown vector, and right side over this here. Okay, for that one, we define this is pi plus 1, and so that is pi. So this is pi plus 1 minus pi. So that is the right hand side. So we have to solve this system of the order degree n-1, dimension n-1, and we decide here from Z1 to Zn-1. Now already we assumed Z0, Zn are 0, so we decided all Z values. Then by using the Z values, we can finalize the formula for the cubic spline. Once the Z values are known, then you can finalize the spline here. Okay, that is for natural cubic splines. Now, how about for clamped cubic splines? We assume that f prime A and f prime B are known. Then the extra conditions can be formulated in this way. For the spline, S prime at A and S prime at B are enforced by using the known value. Now, this value can be used from the equation here, 103. Okay, let's go to 103. Okay, for that one, already we have as I prime. Once I is 1, then S1 is defined here from x0 to x1. That is S1. Then this is A. Now, and then you can use x is x0. Then you can get the corresponding right side along with I is 1, and also that value will be f prime at A, and also here when I is n, then Sn is defined over here x n minus 1 to xn, which is now B, that is Si, okay, no, Sn. Okay, so that when I is n, that's representing this portion, and you can plug x is now B, then you can get some corresponding right side. If they are simplified, then you can have these equations. So here we have n-1 equations for z values, n plus 1 unknowns of z, and we have here two extra equations. The right side right side values are known, and these are combinations of z values, extra two equations. So by using these m plus 1 equations, you can get m plus 1 unknowns of z values. Using that, using the values, again, you can finalize the formula here. Okay. Okay, let's see this example. Find the natural cubic spline for the same data set. We used this data set for linear spline and quadratic spline. Here, if you construct natural cubic spline, then you can see here solid curve, and dashed curve is the quadratic spline, and dotted curve is for the linear spline. For these data points, quadratic spline seems better than here cubic spline. And around here, the overshooting, the local extrema is made, but looks like the same value from the cubic spline and quadratic splines. But for this position, now local minima is made, but the cubic spline has more the lower extrema than the quadratic spline, so that we can say that the quadratic spline is introducing less oscillation for this example. So quadratic spline is better than the cubic spline. Now let's see this example. Now we have a 3 point, x0, x1, x2. That is x0, x1, x2. There are two subintervals. And here we'll try to get not only the natural cubic spline, but also linear spline and quadratic spline for the data. And these are the cubic spline for first subinterval and for the next second subinterval. Okay. Here we have graph for linear, quadratic, and cubic splines. For this example, now cubic spline is the best. In most cases, cubic spline is better than quadratic or linear splines. It has also some optimality property, and in average sense, the curvature of natural cubic spline is not larger than the curvature of the original function. Let's see the theorem. Optimality theorem for natural cubic spline. And some people may say that the natural cubic spline produces the smoothest interpolating function. So you have to be very careful when you are using the smoothest, that word, but this is smooth. The word smooth is given along with some technical meaning presented in this theorem. Let f double prime be continuous on the interval, and we have a partition, and over the partition S is the natural cubic spline interpolating the function f. Then here second derivative squared of S and integration is bounded by the same operation for f. Second derivative is related with curvature, so that in some sense the average oscillation for the natural cubic spline is not larger than that of the original function. So because of this theorem, people say that natural cubic spline produces the smoothest interpolating function. So it's really quite smooth and has really good property, and so that this is quite popular. Okay, this is end of the section. Thank you.